Okay, so welcome everybody to the 5th session on data curation. Just as always, a heads up for the next sessions, which will be the next 2 weeks. I don't foresee any interruption anymore. So unless you hear otherwise, there's going to be 2 more sessions, and they'll be next week and the week after. And then just wanted to tell you that the paper that is describing this whole workflow has been accepted as of last Friday. So it will be in +1 in the next weeks. Right now it's still available on, it's also available on bioRxiv. That was, I think that's the one that we submitted the original version. There's a few small changes, but there's nothing that changed to the workflow. There's not really anything that changed to the description. There's been some stuff has been moved to a supplementary document, and there's a little bit of clarification for a few things, but otherwise it's the same paper. So please, if you use this workflow, if you like it, or if you use parts of it, please cite this paper. And should you use any of my slides, please credit me for it as well, because there's been a lot of effort into making these slides. So then for today, where are we? So just as a quick reminder, in the first sessions, we've been doing our first curation steps where we checked for individuals and markers that might not be giving good results, and removed them from our data set as soon as possible. And after that, we were making sure that our pedigrees are what they say they are, that they're true. And once we know that that was all in place, last time we started with fixing up the rest of our data using any remaining parent-child errors. And so today's session will assume that we've resolved all our parent-child errors. That doesn't mean that all our errors are out of their data set. So today we'll still be looking at single markers and errors in them. And we will start looking at them through linkage. So if we look at the whole schedule of the workflow, we're at session 5. So this was getting our data ready. We've did that in the first 3 sessions, and if your data set's a bit larger, it might take a bit longer than what we've been doing in the sessions. But overall, we were able to get all of this data and clean that up and fix it during the session. So that's something that this part is something that probably takes a day or 2, maybe a little bit more. And so we're now here. We're in the thick of curating. Last time we did the Mendelian inconsistent errors. So now we'll go to the Mendelian consistent errors. And this part is the bulk of the curation. So this, even though it's also only just 2 sessions, this will be take much more of your time. We started at it last week, but we definitely did not resolve all our errors, and that would probably take, even with a small data set like this, a week or so. But once we get to much bigger data sets, this might take a while. I also want to point out that last time we said, well, if there's errors, we make marker call adjustments. And then you see this error going back, which means that after you made adjustments, you have to make sure that you didn't introduce any new parent-child errors. So today we're here. We'll talk about marker order adjustments, but from here, and it's covered a bit, but there's also an error going back to marker call adjustments. So you'll still find SNPs that are having incorrect calls. And even that we are now in this step, once we make marker call adjustments, we have to go and make sure that we didn't introduce any new parent-child errors. So this is kind of a loop process and an iterative process. Now, once we're in this point and we make some changes, we either don't make new parent-child errors, or when we do, they're often only just a few, and they're relatively simply fixed and quickly fixed. So if we make new ones, it doesn't take as long as when we were solving the bulk of them. All right, before we go more into detail about Mendelian consistent errors, I want to start a FlexQTL project right now, and that is because that's going to probably run for 30-40 minutes. So I want to show some things from that project. So rather than us having to wait 40 minutes while the project is running, I want to run it now so I can, while it's running, go over some other stuff. So I shared some files with you yesterday, and I asked you to put them in some in a folder where you keep your FlexQTL input. So for me, I put them in the 8K Apple, and so here are these files I shared with you. If we make a new FlexQTL project, we do that through Visual FlexQTL. So I'm going to start Visual FlexQTL. For me, it's I have a shortcut on my taskbar. Otherwise, you can find it somewhere in your start menu, and by typing Visual FlexQTL, it should start showing up, or at least the folder should start showing up, and then you can start it from there. So once we've opened Visual FlexQTL, and we just have to start a new project, which is under File, and then New Project, just like last time. This time, we'll call it, I'm going to call it Apple CRS, because that's the reference set, so that's the public part of the Apple data set that we'll be using and that I've shared with you. And I'll call it DR, and I'll come back to why it's DR, but you can call it any name that is makes sense to you. And then I'm gonna save it. For me, I'm going to just save it in my FlexQTL folder where I store all my projects for now. I haven't made two separate folders yet for Apple and Cherry, but you could do that if you want to. And then I'm gonna select the folder. And so as I said last time, that will Visual FlexQTL will then create a new folder in this directory that we set to save it in with the name of our project. And then I need my three input files from Visual FlexQTL. With the first is the parameter file. There's another reason why I'm making subfolders, is that this parameter file always has to be called flexqtl.par, and because of that, if you can't save two of them in the same folder. So if you want to have multiple parameter files saved, you're gonna have to have subfolders where you save them in, because you can't have the same one. You can't have two files with the same name in one folder. And unfortunately, FlexQTL only accepts flexqtl.par as a name, so there's no way of changing the name. And then we need a map file, which is the map file I shared yesterday, which is this one. And then the data file, which I also shared yesterday. And then if you click OK, that should load everything properly into Visual FlexQTL. And then I wanted to point out, if I open my parameter file, you'll see that this parameter in the C, which stands for whether the chromosome should be used or not in the analysis. Right now it's saying 1 and then a bunch of zeros. So Apple has 17 chromosomes, and so this means that only the first chromosome is included in our analysis. I don't really want that, because there's a few examples on other chromosomes, so I'm going to have to change that. If you didn't realize that in your parameter file, you can still change it. You can't change it under the settings tab, because this is all grayed out, but we can change it under the markers tab. And the way to do that is to just check all the chromosomes you want to include. And in this case, I'm just going to include everything so that you all get an idea of how many errors there can still be even after you've run all the parent-child errors and you've fixed them all. So once I've checked all this, there's going to be a star at the settings, which means I've changed some of my settings. As you can see now, these are all ones here. So all my chromosomes will be included, but not until I press save, because otherwise my parameter file will not have changed. And if it it's not changed. It will just still be the way I uploaded it, which is only the first chromosome is included in the analysis. So I have to make sure that I save and say, yes, I want to change my current parameter. And after that, we can run the project. And as last time, just my advice, don't make this visual FlexQTL window too big, because once we start running the project, we won't be able to move it around. And so it's easier if it's small, so that we can still have lots of our desktop or our screen that we can click around without having to minimize everything first. So to run the project, we go to Tools, and then we say rerun FlexQTL, and then if everything goes well, which it is doing for me at least, is it will start reading all the data. And if you had a look at it last time, you'll see that this is already going a little bit slower, and that's because our data file is much larger. And then I'll go back to the presentation for now. So I wanted to come back to the sample sheet, which is one of the things we did in the very beginning. I was creating a new sample sheet for our cherries, and we had all these failed individuals, and I didn't want to, and then we rerun the failed individuals, and I didn't want to give the new individuals a suffix like duplicate or anything, because those are the full names and those are the only individuals with good data. So I want to, when I do an index match or when I do other searches and matching with other data, I want to make sure that they have their true name so that they are chosen and seen. Now, my failed sample still also had that, just the exact same name. So in this case, they would have been both called FR034D042. But the sample IDs need to have unique names. And I don't know if I stressed that enough in the first session. If you don't, everything will work fine. But what will happen is all these extra columns that Genome Studio is not expecting, but that you can add if you want, they will just take whichever name they see first, and then they will copy everything for any individual with the exact same name. So in my case, this individual was first, and I had a 1 for poor DNA because it was a failed sample, and suddenly my good sample also had a 1 for poor DNA. And so if I didn't pay attention to that, I would have just excluded my good sample too. So there's a few options you can do. I prefer, and I would suggest that you just add a flag or like an extra little thing at the end to say to the failed samples that they failed, and then you can just safely add to your sample sheet new individuals with the exact same name without having anything else at the end of their name. You could just remove the failed samples from your sample sheet. The danger there is that if somebody comes in, let's say, a year or two, and they're wondering why you didn't include the sample, even though it could be a useful sample, and you haven't mentioned somewhere else that that sample failed, then people might start redoing whatever you did, and that's just a waste of time. So rather than that, having everything in the sample sheet and have annotations to it and saying, hey, this sample failed, hopefully then prevents people from redoing your work. And then I wanted to come back to some clustering issues. Last time I've said that as we were resolving parent-child errors, that that you need to get a feel for it, that you need to like just go in and look at a lot of plots and you'll figure out what is happening. That's still true. There's so many different things I've seen. It's really hard to just show everything because that would take so much time. And I don't think that would necessarily be very useful because you might not even see them and you might come across different things. But I think it is just worth to go over some of the issues that I've seen again and just show you a few more examples so that you already have a little bit more of a feeling once you start looking at your own data. So one of the things in Apple, at least, I've seen a lot is extra groups. And so in this first example, we can see four groups, and the fourth group is not called, or mostly of it is not called. There's a few individuals here that are purple, which means they were called AB, but otherwise they were not called. So that's something that will occur regularly, at least in Apple. And as I've said before, families or individuals with pedigree information are the key to solving all of this and figuring out what this is. So what I would do here is I would select in Genome Studio these individuals and see what these individuals are. And hopefully some of them are of an F1 family. And if not, there should be enough individuals that I have parents for. And then I'll just start looking at what the parents are. And let's say that there is a family here, and I look at what the other seedlings are doing in the family. And let's say that the two parents are in this cluster here. That would mean both parents are AB. That would mean that following normal segregation patterns, that I would expect 25% of the offspring to be AA, 25 of the offspring to be BB, and 50% of the offspring to be AB. And then I just have to see what the other individuals do. So hopefully I'll see some individuals in here, which are the BB. And then might probably see some individuals in here as AB. And then maybe I'll only see individuals in this cluster. And maybe that's about 25% of the offspring. And I won't see anything in this cluster. Well, if that would be the case, then this would be AA individuals. Now, it could be that this is actually an AB cluster and that about 25% of the AB individuals are in here and 25% of the AB individuals are in here. But then we would still see another 25% of the individuals, which is AA. So that would mean that our 50% AB individuals got split up into two different groups, which would indicate that there's actually more alleles than just two in this case. But most likely, if the AB cluster is split up in these two, then one of the parents would also be in this one, is what my experience is. But so it's families that will help you solve these extra clusters. Now, in some cases, it might just not be solvable. Here is a cluster that seems to have, well, at least two here, and maybe this on top is an extra cluster. So there's two AA clusters. There seems to be two BB clusters, and there seem to be even three AB clusters. What this could be, well, it could be that there's one main locus that is being assessed, and that locus is truly AA, AB, and BB. But there might be actually a second locus that is binding to these probes, and it's influencing a little bit our calls. It's not, let's say that locus binds for about 15% of all the probes, then anything for that second locus that is AB or BB, while the main locus is AA, would add a little bit of B allele to our AA individuals, and it would create this extra cluster here. And similarly, it would create all these extra clusters for the other genotypes. And that might still work and might be accurately called, or it might actually be that this SNP cannot be called accurately, or you cannot distinguish between the two loci properly. And there's other SNPs here that might not even be really solvable. So extra clusters, you look at families and you try to solve it. As I said last time, give it about 5 to 10 minutes. If you, after 10 minutes, still don't have the idea that you figured it out, then it might be worth to just remove the SNP. Of course, if you figured it out around 10 minutes and you still have to do all the genotype calls manually, go ahead and do that. It might also be that you think you figured it out, that you run FlexQTL again, and that you find more errors, and that you didn't. And maybe you had two hypotheses and you can test the second one, but after that it might be, if you still don't find it, then it might be time to remove that SNP from your data set. Another thing we saw a lot in Apple, at least, was null alleles. And so null alleles are often characterized by two groups, and in this case you can't really see the two groups, and that would be a good reason to discard the SNP, because if you can't make the calls accurately, then it's just going to cause a lot of pain later on, and you might still have a lot of errors in there even if you don't see them. Now, null alleles are often characterized in Genome Studio by all these X's and O's at the bottom of the AA, either as a separate group, and then it's pretty clear what the null alleles are, or merged with the AA group. So there's these X's and O's, if you recall from the first session, indicate issues with parent-child relationships. And so they are typically found at the bottom because if the null allele is there, it causes lower intensities, and then A null would then could have a B null offspring, and then since genome doesn't recognize it as a null, we'll just see it as an AA offspring for a BB parent or the other way around and call that an error. So those SNPs are often characterized by these signs at the bottom, but you need to make sure at that point that your pedigree relations that you've given to Genome Studio are correct, because if they're not correct, you might see a lot of parent-child errors that are not truly parent-child errors. The other, in some cases, at least for null alleles, you'll see this whole smear of SNPs or individuals better on the bottom. Those would be your null individuals. So they're homozygous for the null and they didn't amplify at all. And they get kind of stretched out on the bottom. And these are some other examples of SNPs where it looked like there were null alleles. In this case, there's not just only null alleles, there's also some extra clusters. So it can get pretty complicated. And again, look at it, and if you think you're solving it, go ahead. But if after 5 or 10 minutes you're still breaking your head over it, it might be worth to remove the SNP. Remember that I think we had about 100 SNPs or 200 SNPs with errors. I think at Apple we had closer to 1,000, 1,500 SNPs with errors. If you take 10 minutes to solve each SNP, that is still going to take you a few months to get through all the SNPs. So I think 5 to 10 minutes is a good cutoff. Other things that I didn't really talk about, I think, are merged clusters. So I've talked about shifted clusters where the 3 clusters, the AA, the AAB, and the BB get close to each other, but in some cases they get so close to each other that, at least from what I can tell from families, is that this little bunch of yellow SNPs, individuals at the corner of the AB cluster, that they're probably BB individuals and not AB individuals. Now, once they are merged and they're truly merged and you can't see the difference, then it's probably worth just to discard the SNP. As long as you can make the differentiation between the 2 clusters, it's probably worth saving them. And here are some other examples of what it may look like when clusters are merged and you can't differentiate anymore between the homozygous, most of the time between the homozygous and the heterozygous. And in this case here, you can actually see 3 clusters, and at least one of those is the AA cluster, but I'm not sure anymore which one if this is also AA or not, but probably not, because if this were both AA, then I think we could have more or less made the safest distinction between AA and AB. And I know that this SNP got discarded. So keep in mind that if you only see 2 clusters, it could be just truly 2 clusters, but there is a chance that your BB or your AA cluster is just merged with everything. And then there are just SNPs that you look at, and even if there's such a spread of the individuals and there's not really anything clearly going on, that you might just decide that, well, there's absolutely no accurate clustering possible, even if I would be able to figure out what's going on, and I just discard them. Like here, for instance, it might be 3 clusters here. This might be a cluster. This lower thing might be a cluster, and then you have the true BB cluster, but really what's happening here, and it's probably really hard to make accurate calls here. So once you see it's really hard to make accurate calls, then it's probably just the safest to remove the SNP from your data set. Now I do want to point out, last time I was saying that as we're making our data files for Excel and for FlexQTL, I'm also making an Excel book where I save everything, because at that point I can make annotations, I can make colors, I can filter things, and I can keep it that way without having to redo that every time I open the file. Because if you save things as a text file or a data file or a CSV file, all your formatting, you will lose it every time you close the file. So if you have your main files that hold your data, you need to make sure that once you decide to remove a SNP, that it probably makes sense, but you have to remove them from all your data files. So it's not enough to just remove them from your data file and keep them in your map file, because Visual Flex will not realize that you just removed the marker, but not in the other one. And that goes both ways. You cannot just remove it from your map and then hope that Visual FlexQTL will look for individual markers with that name and just not read them, because FlexQTL is not reading marker names from your data file. So you need to remove it from both files if you keep one file for your map file and one file for your data file. And there's other things you can do while keeping track. Well, we did it, one, because we knew we were writing the paper, and so we wanted to have very detailed descriptions of what we did and what the outcomes were. On the other hand, for future reference, for when you add new data to your data set, it might be good to just keep track of what you've been doing and why certain markers were discarded, or certain individuals. But the individuals, like I said, we do that I would suggest doing that in the sample sheet. As for markers and other data, I suggest you do that in a separate file. For Apple, we kept one file that has both our genotypic data and our map data, and we called it our master file that holds all our SNP data. And I'm just going to show you how that looks like so you can have an idea of what I mean when I say keep track of your data and what you're doing. So if you remember the FlexQTL input file, you might see here that, well, it's actually what we had last time is more or less this. We had a column with population, a column with individual's name, 2 parents, a nuisance variable, a phenotype variable, and then our genotypic data. Now, one difference here with the file we created last time is that our alleles are split over 2 columns. So as you can see, these are the marker names here, and each marker here has 2 columns rather than 1. The way it was done last time, if we have 1, it's A would be A space B. And so that way you could have both alleles in the same column because you provided this space, which FlexQTL will read as if it's a new column. So this is a valid way too of doing it. Actually, I prefer the other way. That's why I showed you that way last time. Now, I also told you last time that the semicolon makes FlexQTL completely ignore a line. So that means that by adding here the semicolons at the front of the row, we can actually just add whatever row we want. And so some of the things I've been adding to my data file that will be completely ignored by Visual FlexQTL other than marker names. In our case here is SNP type, and I'll come back to that, what that means. There was here an in RosBREED, and that's because Nick, Howard, and I were using the same file, and we were using one big file, but Nick also had his mapping families in there, and some of the SNPs that did not work in a wider germplasm worked well for his families, and so he wants to keep those SNPs. So they were kept in this data file, but then we had this extra row saying whether this marker was used for the wider RosBREED germplasm or only for Nick's families. Other things that I've added here in the past would be 2 extra rows, one saying which chromosome this is and one saying which the position of the marker is on the chromosome, so that when I'm scrolling through these big files, I have an idea what chromosome I'm at, where I'm at. And then you see that we added a lot of extra stuff at the front here, which we would not copy and paste to make our FlexQTL input files, but they help us annotate or help us keep track of our data. For instance, it would be saying, well, here it's saying it's the crop reference set, so that's the public data set for the apple. It would be saying where the individuals are coming from, whether they were seedlings or selections or cultivars, and if we have any other nodes, we would add that too. And then if I want to go back and create a FlexQTL file, input file, data file, I would start here at the top, and I would hold Control-Shift, I press down and right 2 times, and then I would copy paste that into a text file, and I would have my new data file. And so I would create my data files from here every time. I knew this format was working, so I don't have to worry about making the wrong input files, but it allowed me to keep track of a lot of things that I'm doing. And actually, one other thing that we did was, rather than just removing our SNPs from our data set, if I go all the way here to the end of this data set that I have, actually it doesn't end. There's an empty column here, and that's why if I move over one, this is an empty column here, and that's why if I hold Control and Shift down and I select everything, that it stops right at the LZZ column here, where I want it to stop, but after this empty column, there's a lot more SNPs, but those were all the SNPs we threw out. So I didn't really remove them from my data set, I just put them to the side and said I'm not using these anymore. They're failed, they don't work. But for some reason, if I ever had to go back to them, I still have them here. And then similarly for our map file, we've been keeping track, and there's a lot of colors here, and don't worry about those. But what we've been keeping track of is not just the SNP name or the SNP index that we've been using here, but also the full SNP name, the SS number, which is from the database to which the SNPs were uploaded on MCPI, then the linkage group, the position, but that's not it. Because also again, whether the SNP is in RosBREED or not. And then we have some here are the physical positions, as well as if you go here, updated physical positions, because our genomes have changed in Apple. And so, well, we kept track of all the positions depending on which version you are. So this is the positions in genome version 3. This is the double haploid for those who are familiar with all the Apple genomes. So we have all this extra data here on the SNPs we've been using. And then again, and here it's slightly different, but at the bottom are all our removed SNPs. So we just removed them from our data on the top, and we put them all on the bottom. And actually, you can see here, if we remove them, when we know why we removed them, we would say, oh, they were removed for no alleles or because the clusters were merged. So this is a very detailed tracking of what we did, again, partially because we wanted to have all these details for the paper, but on the other hand, if anybody ever comes back and says, oh, this seems to be an interesting SNP, let's say this SNP is, or this SNP, the one below, is it really interesting because I found it in this paper and it's not in our data set. Well, at this point, I can go in and see, well, oh, this SNP, well, we removed it because we found that the AB and the BB cluster were merged. And I don't have to wonder anymore what happened to the SNP and why it got removed. And then we have actually a third file here that is more resembling the visual FlexQTL input file for the map, where it starts with the group, and then as we go through the chromosome and we're at the end of the chromosome, at some point it says group 2, and then it keeps going all the way down over 17 chromosomes. The only difference that I have here is that we added an extra column here saying which chromosome it's on, and that is just for, it makes it much easier to filter, or if we want to quickly know, if I want to quickly know, I'll just scroll somewhere in the middle here of my file, which is marker there is. Either I have to scroll up till I find group and then see which group it is, but now thanks to this extra column, I can immediately see that this is chromosome 6. And then I would just hold Control and Shift down on the top of column B, and I would just press down and left, and that would copy paste it to a text file, and that would be my input file for FlexQTL. So this is how we've been keeping track of our data, just so you have an idea, and you might have other preferences, but it is good to keep track of what you're doing, especially because you don't want somebody to come in a few years and redo whatever you did. It would be a waste of time. So one of the other things that I did was give a SNP type to each SNP. And that is really for further curation efforts. It's going to make it easier, and I'll talk a little bit about that in session 7. And the classification system has changed slightly over time. But I've been classifying SNPs in a 1 to 7 numbering now. It used to be a 1 to 9 numbering. And as you can see, here are the definitions, where one is a SNP that is actually just looks fine. It looks, if you look at the clustering, it's 3 clusters. There's no extra clusters. There's nothing correct. There just happens to be either a few individuals, a few samples that did something wrong, and that is just random, and it's just something. Once in a while, the array will give you a wrong genotype call. But other than that, nothing really was wrong, and it might actually be that those SNPs don't even have any wrong genotype calls. So it just seems to be like a very robust, good SNP. And then 2 would be like there was one cluster that was incorrectly genotyped, but there's no additional clusters, which means there were only 3 clusters. But in those cases, most of the time, the 3 clusters were squeezed together, and that caused an incorrect identification of one of the clusters, but they were easily fixed. So I know that if I see that the cluster is type 2, I have to go in and change it, but I know I can readily do it, and it's very clear to me. And then as we go further in the numbering, the issues get a bit more complex. So number 3 is there are additional clusters. So there's 4 or 5 clusters, but none of them are null alleles. So I don't have to worry about null alleles in those. I just know that some of the clusters that were there are additional AA or AB or BB clusters. Then number 4 would be there's null alleles in this SNP. Then 5 would be everything seems to be accurate. Everything is going well with the genotyping. Unfortunately, I cannot put it on my genetic map accurately. It keeps giving issues in my genetic map, and we'll come back later today. You'll see what that means, but it just means that we have to remove it from the map, not because it's wrongly genotyped. It doesn't fit our map. And maybe if we get more individuals or a better map, we could add this again in. But right now, unfortunately, we have to remove it. And then 6 were monomorphic SNPs, which means they have only one. They're only AA or BB, and they are not providing any information. So they were removed from our data set. And then 7 meant that, or means that SNPs have failed. For whatever reason, we consider them failed. It's actually the group 7 is a combination of 2 old numbers. It used to be, I think, 6 and 9, where 9 was failed because assist said it was failed, and 6 was failed because after assist, it was approved by assist, but then afterwards we figured it failed. And group 1 was also split into 2, where 1 was no incorrect calls at all, and 2 was a few incorrect calls. But I then realized that the few incorrect calls were just random, and so any number 1 SNP could just by chance or randomness be a type, could be one with just a few wrong, and so I grouped them together in one cluster. And then you can see that I kept track of all these numbering, and this is the old numbering system. And like you see here, a few where it says 1, 5, and 1 meant there's no issue, but 5 at the time meant additional cluster. So basically that meant everything is called correctly, just be aware that there's extra clusters for this SNP, and it might cause an issue with additional germplasm, but right now it's not causing any issue. And just having that system just makes it easy that when I get new individuals in or new data in, I can really relatively quickly get a subset of SNPs that are really good, and for other SNPs I know what's going on and I know how to fix them rather quickly, rather than having to figure it out time and time again. So then to the Mendelian consistent errors. What are Mendelian consistent errors? Well, they're errors that do not infringe on Mendelian law, which is saying that an offspring gets 1 allele of each parent, or each parent is giving 1 allele to its offspring, at least in diploids. And for instance, if you have an AA parent crossed with an AB parent, and you get an AB offspring, that all looks fine. You would not get a parent-parent-child error for this, but actually the individual was AA, the offspring, and it was not AB. So it's still an error. We wouldn't have detected it so far. Sometimes when you get these kind of things where the offspring is called incorrectly, all of the offspring might have been AB here, and that could be because some clustering issues were not all individuals are called correctly, and so all AA individuals would be in this group and would be called AB. Now, in that case, the parent here would also be called AB, but I've seen it where there's a fourth cluster and the parent is in the correctly called AA cluster, and the second cluster is actually also an AA cluster and not an AB cluster, and that one was called incorrectly. So incorrect calls could lead to this kind of errors that you don't even see that are errors. Now, it's not as easy as to just go and look at crosses where AA cross AB gives only AB, or AB cross AB gives only AB. Because sometimes there's true segregation distortion, and I've used the S locus already a few times as one of the loci because it's probably the easiest to understand. But the self-incompatibility in apple, if the father shares an S allele with the mother, then gametes with that S allele will never fertilize the egg, so you will never see that S allele from the father being passed on to the offspring. So you would only see one of the two S alleles being passed on to the offspring, not the other. So that's a true segregation distortion where only one of the two alleles of the father is passed on. But there's other regions in the genome where that might happen because of semi-lethal or lethal combinations of alleles. On the other hand, also, we in RosBREED at least, we're working with small families. So if you have a cross that has 6 offspring and you see one individual having the AA, like the cross that is here in the PowerPoint, and the 5 others would be AB, well, that's in the AA cross AB, you would expect 50-50, so you would expect 3 and 3, and now we see 1 and 5, you might even see 0 and 6. Is that truly a segregation distortion, or is our population size just too small to even detect distortion? So it's not always that easy to just work with segregation distortion, because you'll be looking at a lot more SNPs than you actually need to do. So we need another way to figure it out. And the way to figure it out is linkage, because our alleles and our loci are not just all independent. Our alleles are on chromosomes, and chromosomes are physical molecules, which means that our loci are physically linked to each other. And if in a diploid species at least, we'll have 2 copies or 2 homologs of each chromosome. So we have 2 copies, and those 2 copies might differ. Those are the ABs that we see on our SNP array. And so if we look at 2 loci that are linked physically that are on the same molecule, and for the first SNP or the first locus, we have an A allele and a B allele, and for the second locus, we have a C and a D allele, our alleles are going to be physically linked. And in this case, our A allele is linked to a C allele, and our B allele is linked to a D allele. So we expect, as this parent will give either one of these homologs to the offspring, that in most of the cases, at least, once the offspring gets A, it will also get C, because these are physically linked and they're on the same molecule, and similarly for B and D. Now I say usually, because in meiosis there is such a thing as crossover and recombination, where these 2 chromosomes exchange material, as depicted here in the figure, and so sometimes this linkage may be broken, and if that happens in this case, our offspring, in this case, the A allele would become linked physically to the D allele, and the B would become linked to the C allele. And so you get new chromosome, you get new combinations, new molecules that are a combination of the 2 parental chromosomes. And actually, this process is what we've been using, or what people use to create genetic maps, because if you have one of those recombinations between 2 markers in only 100 gametes, then we say that they are 1 centimorgan apart. So if you see 2 recombinations, you would say they're 2 centimorgan apart. And so that's a measure of how far these 2 loci are away from each other. Because if these breaks are completely random, you can imagine that the farther away these 2 are, the more chance there is to have this break between them. So that's how we've been using our genetic maps. But we can also use that to detect errors. Now, a double recombination, which means 2 recombinations, would mean that there are 2 breaks happening. Now, that does occur. But when we are looking at short distances, and for instance, marker A and marker B are 2 centimorgan apart, and then we expect only 2% or 2% chance of a recombination between the two. Only 2 in 100 gametes will show a recombination. The same goes for marker B and C that are 2 centimorgan apart. There also is a 2% chance of recombination. And if we assume that A and C are on the different side of B, then A and C are 4 centimorgan apart. And the chance that we see 2 recombinations happening there is actually only 4 in 10,000 gametes. So it's a very small chance that we would see a double recombination over there, at least over short distances. So seeing those in our data set, and FlexQTL looks for those, is an indication that something might be going wrong. And why is that? Why? Because as I said before, there's going to be segregation distortion, but some of that could be true. But if we see segregation distortion, we're actually expecting that it's happened to linked markers as well. We're not expecting it to be just happening for a single spot. We're expected to happen for a larger chunk of a chromosome if that's happening. So if we take this example here, where we have 2 parents, and one parent is homozygous for 3 loci and it's homozygous A, well, at that point we know that it will always pass on the A allele to its offspring. We wouldn't even be able to detect any recombination happening because we can't differentiate between the 2 alleles. But so as you can see here in the offspring, there's always this AAA that's coming from the first parent, which has a small black line. And then but the second parent is heterozygous for 3 loci, blue, green, and yellow locus, and they're AB. And as it happens to be in this example, just to make it easy, all the A alleles are on the same physical chromosome. They're all on the blue one, and the B alleles are all on the second homolog, on the purple chromosome. So if we just look first at the blue and the yellow marker, which are having a normal segregation that we expect AA cross AB gives about 50% AA and 50% AB, then anytime an individual is AB, we can know for sure that this B allele must have come from this parent, and as such that it must have gotten the purple chromosome. So that's why here next to this B, this part is purple every time there's a B. And similarly, when the individual is AA, the A allele, well, the second A allele must have come from this parent, which means it must have gotten the blue chromosome. And so that's why both up and for the blue and yellow marker, when there's an A here, this stretch is colored blue because it's the blue chromosome it inherited. Now, this marker, this third marker that is lying in between them, between the blue and the yellow one, is also an AA cross AB, but we only see there that all the offspring is AB. Now, with the same logic as there, we could say that the A allele must have come from this parent, and so every time we see a B allele, it must have come from the other parent. And in this case, we know that the B is on the purple, so the only way to explain that all these offspring have a B allele is by saying they inherit the purple part of the purple chromosome for that area. Now, for the first and last offspring, that's okay, because you see that the whole chromosome is in a purple chunk. For the 2 in the middle here, the only way to explain this behavior for this marker is by saying, well, it must have gotten the blue chromosome, then the purple, then back the blue. And so you can see that these segregation distortions here, if it's happening to linked markers, they will force a double recombination here, because to get to this, you need to get from blue, recombine to purple, and recombine again to blue. So markers that are not truly having a segregation distortion, but just incorrect calls, lead to double recombinations, and that's what FlexQTL is detecting. So that's what we'll be using to look at suspicious markers. Now, the other thing I wanted to say here is, by knowing that this is purple and this is blue, what we're doing is, well, we know where this is coming from in the parent, but actually we are actually also knowing from which grandparent it is coming, which basically saying that because this individual got each of their 2 chromosomes from one of its parents, we know that in this individual it got the blue, which came from this parent, and this came from grandparent 1. Whereas if it gets the purple one, we know it still got it from this parent, but now we know it got it from grandparent 2. And that's just important to understand some of the FlexQTL output files that are being created, which are called GPO output files. They're called, and they stand for grandparental origin. So those are files that FlexQTL creates to keep track of like where chromosomes are coming from or segments are coming from. We won't really use them a lot right now, but in case when you'll be using FlexQTL a lot, you'll see those files and you want to maybe look at those. So just those are GPOs, and those are basically saying those are used to figure out which alleles are on the same chromosome physically. So the other point I wanted to point out before we start is that we need to know which markers are linked to each other, so checking for double recombination requires a map. Now, already last time we used the map, but it's important to know that as far as I know, FlexQTL did not really use that map to look for parent-parent-child errors. It's just looking within a single marker, and we could have just put all markers on the same chromosome, and it wouldn't have mattered because FlexQTL is just looking across one marker, and it's not taking flanking markers into account, at least not for parent-parent-child errors. Now that we are looking for double recombinations, we do need accurate maps. So I've already explained last time how we got to maps, which is either because we have large F1 families and we've figured out which alleles are linked and which markers are linked, or because we're using a genome as a template. Now, it's also important to notice that we might actually have errors in our genome, especially if we use a physical genome as our template. It might not be assembled completely correctly. And if markers are put in the genome somewhere and they're not truly there, and we put them in our map and they're not truly there where they should be, then that could also lead to double recombinations. And that would not mean that our SNP is called incorrectly, it just means that our marker is not where it should be in our map. So while checking for double recombinations, it's a bit more complicated than just looking at incorrect genotype calls, because it might also be a map error. On the other hand, while we're doing this, we're also improving our map, which is also a really great thing. And so as I said before, FlexQTL has to assign which alleles are linked to the same physical chromosome, which is called phasing. And so FlexQTL is doing that for us, and I'll get back to that a bit more in the next session. But so just be aware that FlexQTL is doing that phasing and deciding which alleles are on the same chromosome, and it actually also might make errors there. So why did we wait for looking for double recombinations up till now, and why not earlier? This is a part of a table from the paper, and there's a bit more that it's just a small part of it. But what it's saying here is saying there's a lot of reasons why you get errors. And as we've gone over this sometimes, I hope now, we have parent-parent-child errors, and they could be caused by just incorrect callings, just SNPs that don't work well. They could also be caused by low sample quality. They could also be caused by incorrect pedigree, and because we're thinking something as a parent and a child, we'll get a lot of errors. Now, they're grayed out because once we start looking at parent-parent-child errors, they should have been taken care of mostly. So what really remains is incorrect clustering, and either incorrect clustering or just a few incorrect genotype calls, not due to clustering. Now, for the double recombinations, all of these issues that we've been dealing with before are also causing double recombinations. So the more we take care of them early, the less we have to look at this. And it's always, and actually the workflow is set up in a way that we deal with the easy problems first and then go to more complex issues. So one extra thing that is causing double recombination might be a triploid in your data set when you're expecting diploid individuals. And that is because there's actually a third chromosome set, and that's just causing that phasing. Deciding which markers are physically linked is not going to be accurate if you have 3 molecules and you're trying to distribute the alleles over only 2. So that's one of the reasons we threw out ploidy in the beginning, because they're going to cause issues otherwise now. And then, as I've said, there's not just genotype calls, there's also marker positions and phasing. So solving double recombinations is more complex than solving parent-parent-child errors. So the more we can get them done earlier, the more issues we resolve, then the easier it is for us here. And this is another figure which is showing the map for Apple with its 17 chromosomes, and there's a big gap, and just ignore that gap here. But what it's showing is the red dots are the double recombination frequency. So we expect that to be very low because we don't expect a lot of double recombinations. Now, as you can see here, you can see that actually these frequencies are throughout the map are pretty high for a lot of loci, which means that there's a ton of double recombinations reported. And that was before any of the parent-parent-child errors were resolved. Once we resolved all the parent-parent-child errors, there's still a decent amount of double recombinations here that are issues, but I hope you can clearly see that there's way more here than there are here. And I don't have the numbers by heart, but I believe that at this point the double recombinations that are reported is it's a few thousand here, whereas here it was in the tens of thousands and maybe even close to 100,000. So that would mean that if you just started with double recombinations, you would be checking tens of thousands of issues, whereas now we're only checking for a few thousand issues. And if you remember that the parent-parent-child errors itself were maybe 1,000 issues, then 1,000 plus a few thousand is still 3,000–4,000 issues to check, whereas tens of thousands is a lot more to check. So you'd spend a lot more time on fixing all of this, which is not necessary. So if you would just wait till you get to this step and you've just first resolved all your parent-parent-child errors. So that's a big reason why we're doing the order that we're doing, is to minimize time needed to go look at all the errors. And then I'll see if FlexQTL has stopped running or is done with running. Yes, it is. So to properly show recombinations and double recombinations, we'll look at this at the segregation indicator pattern tab. But most of the time I've found that it doesn't work right out of the box after a run. And the only way to make it work is just close the project, start Visual FlexQTL again, and then rather than saying new project, you can open a project and go to any project you've run before, and it will automatically tell you to open the last project you run. So in this case, that's the project I want. So you can just click on that parameter file. I'll do that again. So under File and Open Project, you'll get the option to, as a parameter file, to open that project, the project, and you do so through the parameter file that's linked to the project. And then if you go to segregation indicator patterns, this will now look correct. And to see recombinations and double recombinations, you have to here under this drop-down menu, look at recombination sequences. And if that goes well, we now can see our recombinations. And I'll explain this file a bit to show you, but let me first zoom out a bit. So what is happening here is Visual FlexQTL is showing us all our individuals, and for each individual it is now given 2 lines. So this first individual here, and as every other individual, has 2 lines, one for its mother and one with saying its father. So these are the 2 parents of this individual. And so what is listed here is showing which chromosome it got from this parent, and then the second line is saying which chromosomes did it get from its second parent, so in this case the father. And then there's 2 color codes, blue and yellow, and blue means they're indicated by a 1 or an S1, means that these alleles, they came from this mother, but the mother got them in turn, this mother got them from her father. So this means if it's blue, in this case it would mean it's coming from a grandfather, and in this case it would be from the maternal grandfather. Similarly, here, the second chromosome of this individual is coming from the father, and given that it's blue again, it means it's coming from the grandfather on the father's side. Now, if it's yellow, which is indicated by zeros or S zeros, it means that it's not coming from the, it's coming from this parent. So in this case, it's coming from Honeycrisp, but then it's coming from the mother of Honeycrisp. So yellow means it's coming from the grandmother. If FlexQTL does not, if let's say we don't have the parents of this and we can't figure out whether it's the grandmother or the grandfather, FlexQTL just will make an assumption. So be aware that at the top of the pedigree, it might not always be truly from the grandmother or the grandfather, but this is still showing which alleles are linked. Because as long as this is all yellow, it just means it's coming from the same grandparent. And that is then what is changing here. And these are a bit long. If you look at this orange, is where it's showing a change. So for instance here, this one individual was from Honeycrisp was getting a chromosome segment that came through the mother of Honeycrisp, and then afterwards, at this point, for chromosome 1, it was getting a segment that was coming from the father of Honeycrisp, so it was coming from the grandfather. So the only way to explain that is by saying, well, somewhere here in this area, a recombination must have occurred. We don't know where, because all these markers with a dash, we can't distinguish between the two chromosomes of Honeycrisp, so we can't distinguish whether it came from the mother or the father from Honeycrisp. So that happens when our alleles are that happens in this case when Honeycrisp is homozygous, so it's AA or BB. At that point, we cannot determine from which on which strand it was, on which homolog it was. But for this marker, FlexQTL could, and for this marker, FlexQTL could, and so it knows that somewhere in between here, a recombination must have occurred. So the S's in front of the 0 or the 1 just means that it's putative. It's not 100% sure, but most of the time it will be accurate because it will. You see that here is a 0 and here is a 0, so it's very likely that this is a 0. I think FlexQTL is not 100% sure when you have many generations of AB, because that makes it really hard to figure out where things are coming from. And then you see already here something in red. And if you look at this, you can see that this goes from 0 to 1 to 0, which means in this case there's a double recombination, because to get from 0 to 1 you need a recombination, and to get from 1 to 0 you need a recombination. So this is a double recombination. And if we look at this, this is happening at 15.45 centimorgan. So I forgot to explain that. What you see on the top is all the marker names, and then their position on the chromosome in centimorgans. So this would be at about 15 centimorgans, if I did that right, and this one is also at 15 centimorgans. So that means that in this interval of less than a centimorgan, we see 2 recombinations, which is very unlikely, and so FlexQTL is highlighting this in red to say, hey, something is going wrong here. And that's how you read this visual output of visual FlexQTL. Now, you could just go and look through this whole map, and that would take a while because there's a lot of individuals and there's a lot of chromosomes. So there's better ways of finding our double recombinations, but this is a way of visualizing double recombinations. The only disadvantage here is that on the top, it does not say which chromosome we're at. And so if I scroll to the right, we'll go over chromosome 1. And at some point, you'll see here, as we get higher in the position, this will change from yellow to dark orange, and then at some point we'll be back at yellow, and this is where the next chromosome starts, which you can also see because the position starts back at 0. But there's no way of knowing which chromosome you're at other than just counting the chromosomes as you're sliding, and then you need to make sure that you don't go too fast. So FlexQTL, there's 2 ways of reporting double recombinations by FlexQTL. The first is a file that is automatically generated as we make a run, and it's called double recomp. And what that does, it is reporting all singletons. And a singleton is any time only a single marker is involved in a double recombination. Now it's a single marker with known chromosome segments. So a single marker that has a 0 or a 1. So in this case, this would be a singleton because you go from 0 to 1 and you go back to 0. And there's only one marker, one SNP here that has a 1. So there's only one SNP for which there is a change. There is a second SNP here, but we don't know what that SNP is. And so because we don't know, it doesn't count. And so there's only one known SNP involved in this double recombination. So that would be a singleton. And FlexQTL will report all of them. Now, as you can see here with the orange ones, you can see that there could be large stretches of unknowns. So FlexQTL will also report singletons where there is a long stretch of unknowns to the left and a long stretch of unknowns to the right. And I've seen instances where there's only one marker that we're sure of, and then a lot of markers that we don't know, and then a recombination. So a double recombination that actually stretches a long interval. And the longer that interval becomes, the more likely that is actually a true double recombination. If that's 20 centimorgan one way and 20 centimorgan the other way, it's a 40 centimorgan interval over which a double recombination occurs. It's still worth checking it out, but if you don't find any genotype call errors, it doesn't seem that there is a map error, then one of those might actually be true double recombinations, just because there's such much uncertainty that FlexQTL still reports it in that file. So I'll come back to that file. I'll just say what the other type of double recombination is when there's multiple markers involved. So if this would be 0, 1, 1, 0, then we have two markers with a 1. And at that point, there's more than one marker involved in the double recombination. And so FlexQTL, what it does, it reports all double recombinations, so not just the singletons, but also the ones with multiple markers involved in a separate file, and we have to generate that file because it's not a standard output of FlexQTL. And to do that, we go to Tools, and the first thing we'll do is say recompute recombination sequences. And what this is doing is telling Visual FlexQTL or FlexQTL what is my limit for suspicious double recombination. So right now this is set at 10 centimorgan, and I think that's a good threshold. So what this means is that FlexQTL will report any double recombination within 10 centimorgans. Anything that's larger than 10 centimorgans, it's not going to bother. It's going to assume that that's okay. I think that 10 centimorgans is a very good threshold to begin with, and I think that that's the one I've been using, but if you want, you can set it higher or lower. So if you want to set it, if you would want to say it differently, you would change this and then click OK, and then it will have that as a new threshold. And that will also reflect how it's shown here, because then everything right now it's only showing things as red as double recombinations when it's sorry, below the threshold. So to create that file, then you go to Tools, Export, and export recombination sequence file, which then will report all of our double recombinations within the given threshold. And then it's asking where do you want to save this file, and most of the time I just save it in the run that it comes with. And just need to say select a folder. I can't choose the name. It will give automatically a name to that file, and that file name is double recombinations. So there are two files: the double recomb file, which is showing all the singletons, no matter what the interval is over which they occur, and this is showing all double recombinations, but only within the interval that you asked for. And so let's have a look at both of the files. Let's start with the singletons file, which is the double recomb file here. So this is what it looks like. And what information is here? Well, this is listing all the singletons, as I said. And so if I quickly scroll to the bottom of the file, I'm holding Control and pressing down. You can see that there's 5,130 double recombinations reported here. But as I said, some of those might be true. Then, what is on each line? So I guess one of the things here is the ID, which is saying in which individual did the double recombination occur. So in the first line, the recombination occurred in delicious. It's saying which is the parent that gave the chromosome on which a double recombination occurred. So in this case, it's WINSEP each time that gave the chromosomes on which the double recombination occurred. So if you want to start finding this, you would scroll in this. Either you scroll here in this file till you find delicious and the line that here says WINSEP, and then you would know you're on the right line to look for the double recombinations. So there's other ways of filtering. I'll come back to that in a second. So to more quickly go to the correct line you want to have. What else is happening here? Here, this is saying how the double recombination looked like. So it's saying it's a 0 became a 1 became a 0. So that's the same as how it was shown in Visual FlexQTL. So these are those zeros and ones that directly link to what can be seen in Visual FlexQTL. Then here it's saying the marker position in the map. So 807 means it was the 807th marker in our map. And then that was where it was still a 0. And then the first marker where it was a 1 was the 825th marker. So you can already see that there's 20 markers more or less in between that FlexQTL didn't know anything about. So that could 20 markers that, depending on our map, that could be a few centimorgan or that could be 10 centimorgan. So that's something we would have to look at because that is not being given here, how large the interval is. And then the next locus is just saying what the number of the map, the next marker is for which it was certain again that it was a 0. So you can see that it's again about 20 markers away. So this is actually a pretty big gap for a singleton. It might actually be a true one if this is over a large enough distance. Then here it's telling us the names of these 3 markers involved. So this is the last marker that was a 0, is marker 2512. This is the singleton marker, the marker around which the double recombination occurred. And then this is the first marker again, that is the 0. And so that's how these are reported. And then we'll go to the other file, just have a look at how they are reported because it's slightly different. And that's the double recombinations file. I'll open that. So what do we see here? There's the information is slightly different. So here it's saying for which individual a double recombination was observed. It's telling us on which chromosome. Now it's saying the homolog, which is not 0. It's not saying 0 or 1. It's just saying it's not showing how it went from 0 to 1 to 0. It's just saying it's 0. And I believe my experience is this just means that 0, that it's on the homolog coming from the mom. And if this is a 1, it means it's on the homolog coming from the dad. So it's not telling us which parent. It's telling us which parent, but it's not naming the parent. So we need to go and look into which is the mom and which is the dad to know, to really know which parent gave the chromosome that, or which individual gave the chromosome that the double recombination occurred. And then you get 3 M's, which are the marker names. And so what's happening is that there's a crossover, or recombination between marker 1 and marker 2. So in this case, between marker 3367 and marker 8765. And then the second recombination is occurring between marker 3 and 4, which in this case is marker 8765 and marker 5276. And so as you can see here, marker 2 and 3 are the same, which means in this case, this is a singleton. But it's not always the case. For instance, here, there's 2 different markers involved, which means there's a double recombination going over at least 2 markers, but it might be even more. And then P1 to 4 are the positions of these 4 markers. So We get a lot more positional information in this file. We don't necessarily get which individual, which parent it come from. So it's slightly different. And then this gives a suspicion level, saying how suspicious is this, and it goes from 0 to 1, and 1 means very, very suspicious. So where do we start? Because even this file, if we look at this, there's even more double recombinations reported here. There's about 6,400 reported. So that's a lot of things to look at. So how do we start? Where do we start? My advice is to start with markers or regions that have a lot of double recombinations in that specific region or marker. And I would suggest that you start off with the singletons, but not just all the singletons. If we go to the singletons, there's a few things we can do here with this file. Well, one is I would save this as an Excel file so that whatever we do, we can make annotations to this file again, and we can keep track of what we're doing. Other than that, I'd say let's have a look at which markers are really involved a lot in double recombinations. And how do we do that? Well, the easiest way is to say use a formula using count if. So if we're doing a count if, and we're looking at these markers, which as I said, these are the markers around which a double recombination occurs. So there's a recombination left of this marker and right, or upstream and downstream of this marker. So I'm saying I want to see how often a specific marker occurs, how often a marker has a double recombinations around it. So it's this marker, the current name one that I'm looking for, and then if I want to know how often it occurs for this marker, I just say as my criteria, this marker with this name. And then you can see that this marker only has one double recombination around it. Now, if I do this for all, if I drag this down and I apply the formula to everything, you can already see that there are certain markers that have a lot of double recombinations around them. And as I've said before, a double recombination might occur, but 72 around a single marker, that's very, very suspicious. So I would start with these. Now, before I go look more into this, I want to have a better idea of where these markers are, because right now I barely have any idea where they are. So to do that, I shared another file yesterday with you in the FlexQTL input file, which should be here, which was mapped with chromosome. And as that is opening, you will see what this is. This is our map file, but now I have the chromosome number next to each marker, and that will make it really easy for me to figure out where a certain marker is located. So as before, if I want to figure out what the chromosome or the position of this marker is based on another table, I'm going to use index and match. So when I use index, I want to know which chromosome it is, which is in column D. And then I want to match this SNP to the names in column B. And again, I want an exact match. I don't want to approximate maps. And now I can already see that this marker is on chromosome 3. And now I can do the same thing for the position with an index, which position is in column C. And then again, I want to figure it out for this marker, and the marker names in this table are in column B. So and again, I want an exact match because I don't want, if I'm looking for marker 2014, I don't want the results from marker 2013. And so now I know that this marker is on chromosome 3 and position of around 37 centimorgan. And then I drag this formula down so that I know it's for all the markers. And as always, I'm going to just replace my formula by selecting everything. And again, I select everything by holding down Control and Shift, and I just select, pressing right and down to select everything. I hit Control C to get a copy, and then I right click here and choose paste values. And at this point, everything is fixed, and now I can sort my data table here, and I'll just make this larger again. And I can sort my whole data table, select all the values that I have, and then I hit sort, and I want to make sure my data has headers because this part is all names of my columns, and I haven't given a name to my new columns, but I want to first sort it on M. And if you recall, M is how often does this marker occur. So, and I'm not interested in the ones that only occur once as right now. I want to see the ones that occur a lot. So I'm going to filter it from largest to smallest. And then, should there be multiple markers with the same that occur equal amount of times, I just want to group everything, all the same markers. And so I'm just going to look at them chromosome by chromosome if that's the case. So I'm just going to sort on column N, which is the chromosome number, and then should there even be multiple on the same chromosome, I want to just sort them chromosome by chromosome going up. So I'm just going to sort them according to their position too. And so then we can see here that there is the first marker, which is marker 8002, which is occurring 96 times in our data set. So of our 5,000 reports, we can already, if we solve this marker, we already solved 100 double recombinations. And you can already see that often it's Honeycrisp, it seems to be Gala, I already see a few times, I see Greyburn, I see Pinova, I definitely see Honeycrisp a lot. So you can see that's happening for the same parent over and over again. So this one would be a good one to solve first. You don't have the Genome Studio project, so I'll just show you what it looks like. This is what marker 8002 looks like. And so I hope you by now are a bit familiar with these plots, and you can see what's happening here, that there is the clusters are shifted, and that at least the BB cluster is probably not called correctly. This is the BB cluster, and that might not have led to errors anymore, but it surely leads to double recombinations. And so what we would do for this one is recall this, and then this should solve our double recombination issue. So the first thing I would do, especially for markers that have a lot of double recombination, is just go and look at the plots. This marker 7544, if I look in this file, it's going to be down here somewhere. Here it is, 744. You can see it's occurring 80 times in our data set as a double recombination. And again, if we look at this plot, there's clearly something going wrong here with the clustering calls. So if you want to look at those markers and see what's happening in Visual FlexQTL, let's go back to the one on 8000. This one is on chromosome 6. So as I said before, there's no easy way to know on which chromosome you are, unfortunately. So we would have to go and scroll and count the numbers it changes. Now, if you do that too fast, then you might miss some, and especially for chromosome 11 or 12 or some in the middle for Apple, that might take a while. So what I mostly do is I make an educated guess of where it is. So chromosome 6 is about 1/3 of all the chromosomes, so that would be somewhere here, let's say. And then I look, I look just at any marker, and let's just take this marker, marker 5260, and I go to my map, just 5260, and I only want marker names, and I look, and this is on chromosome 5. So I need to move over one more chromosome, but at least, especially for the middle ones, that is faster than slowly sliding till you're at where you're at. And then it was marker 8002, if you recall, and you can already see that there's here a lot of issues. And well, because we know that the issue is with the clustering, I'm not gonna look for other solutions right now. I first want to fix the clustering and hope that that fixes everything. So let's go back to the beginning and back to our file here. So what you would be doing here is, at least for the ones that occur a lot in the data set, just solve these singletons first. I would say anything, it depends a bit on how big your data set is, but anything that occurs a good chunk, and a good chunk, I would say anything that occurs up to 50 or 50, maybe 40, just have a look at those. And then after you've done all the ones that occur at least 40, maybe you could take a break. And if you do that, you can see you've already probably solved, you would have solved about half of the singletons at least that are reported. And what I mean when you can take a break is, once you've solved a bunch of these double recombinations, what you want to do is rerun Visual FlexQTL and see if you truly solved the double recombinations, and maybe and that's important because as you're solving double recombinations, sometimes, and I'm not sure if I have an example here readily available, but sometimes when you, here for instance, let's just say this goes from 0 to 1 to 0 to 1. Now, if you, and we can see that this marker is involved already 2 times here. So let's say we solve this marker here and we figure out that this actually, and we solve it in a way that this becomes a 0 and this becomes a 1. At this point, the second double recombination is solved, because once this becomes a 1, it's going from 0 to 1 and then it stays 1. And the second double recombination is not a double recombination anymore at the time. So by solving some double recombinations, and especially the ones that occur a lot, you might actually already solve some that only occur once in a while. Now, the disadvantage of working with singletons is that if you solve it, you sometimes actually create new singletons. So here you can see there's multiple involved here, so this might not be the best example, but let's say we solve these 3, but let's say that, no, it's not a good example, but let's say you have only 2 here. And one of those 2 is a singleton somewhere else, and we fix it, then these 2 become 1, and this 1 that remained was not, these 2 were not reported earlier because there were 2, and so they were not a singleton, but by solving one of them, the second one suddenly stands all alone, and because it stands all alone, it becomes a singleton, and so it becomes reported at the time. So what that means is solving singletons might fix a lot of other double recombinations, but it might actually introduce new singletons as well. So once you've solved the really big singletons, or is it, once you've solved the ones here, the big ones, the ones that occur a lot, you might want to move towards areas where there's double recombinations that involve multiple markers. And for that, we would need this file. And there, I would just suggest that you do sorting as well, but it's, given that there's multiple markers involved, it's a bit trickier which marker to sort on. So rather than sorting on a marker, I would sort on a position, and I would first sort it by chromosome, and then I would add a level here, and then I would sort it by the position of the second marker, because remember that there's a recombination between marker 1 and 2, and then recombination between marker 3 and 4. And sometimes where there's multiple markers involved, the first marker that is involved, the first one that is reported here is this one, but for this stretch, it's this one, and maybe for another stretch here, it's this one. And so the start marker might actually vary, but the double recombinations that occur might be occurring around the same markers time and time again. So it's the center of our double recombination that is more fixed than our start or end boundary, if that makes sense. And so by looking at position 2, we're more filtering on the center of our double recombination rather than on the position of the start where it started. So I advise to sort on P2. You could also sort on P3, which should give similar results, but I would sort on either P2 or P3. And now everything is sorted by chromosome. And then as you're going through this, we can already see here that there's a lot of recombinations occurring around 15 centimorgans on chromosome 1. So this might be, once you've sorted out the biggest singletons, this might be one of the things you start looking at next, which is here areas where there's a lot of double recombination. And as well, some of these are singletons, but some of them are not. And so you might want to go and look at that and look what's happening there. So from my experience so far, I've only talked about cluster issues. When is cluster issues, or how do we recognize cluster issues by double recombinations? It is, well, they're characterized by things that do not lead to parent-parent-child errors, or otherwise we would have seen them before. But what happens is we see a lot of double recombinations for a single family or a few families, and that's because individuals of those families are clustered incorrectly. And that's why we see them. And we see them regularly because at least half or 25% of that family is just called incorrectly. So we see them regularly for a family. Another thing that happens when clustering is an issue is that it's always the same parent involved. And that might actually just be that that parent is called incorrectly. And because the parent is called incorrectly, we get all these double recombinations in the offspring. And then the one that is hardest to find is similar to the one where the parent is incorrect, but in that case, the parent has missing data. FlexQTL imputed something, but imputed it incorrectly. And because it imputed it incorrectly, a lot of the offspring of that parent get double recombinations. So if you see that happening, you need to impute it yourself basically and fill that missing data point in if you can, so that FlexQTL won't determine it, make an incorrect call there. But clustering issues or genotype issues are often characterized by multiple double recombinations in the same family, and all because of a single parent. Now, there are other issues with double recombinations, and that is our map. And actually, I'll show you a real life example. If you can find it again. It's at the very beginning, or and it's in a parent that is, it's only happening in ginger gold as a parent. So I said before, I come back to filtering. You can filter these columns, and the filtering looks very similar to what's happening in Excel, although it is not. So if I want to filter here for ginger gold, I could say, oh, it's here. And if I would select OK at this point in Excel, I would only see my ginger gold offspring. If I do that here, I clicked OK, nothing happens. Why is that? Because even if I'm looking through all these by filling in ginger gold, everything else remains selected. So what I need to do first is to make sure everything is unselected, then look for ginger gold, and then only select ginger gold and say OK, and then I'll have filtered. And so the next kind of issue you'll see with double recombinations is map issues. As I've said before, there might be things wrong with our map. Those are often characterized not by a double recombination, but a triple recombination. So you can see here it goes from 0 to 1, which is the first recombination, from 1 to 0, which is the second recombination, and then back to 1, which is the third recombination. So I can't move around here in Visual FlexQTL, but if I would remove this single marker here that has the 1s, and I move it all the way up to here, after this 0, then we could get one stretch of zeros and then only 1s. And that would just be a regular recombination and not a double recombination. So by moving this marker in my map to a different location, I could solve 2 double recombinations right now, because this is one double recombination and this is the second. So they're both reported. That's why our files sometimes get very large with reported. But by moving this marker, I would solve 4 reported recombinations, 2 for each individual. Now, when I if I go back to the Excel file, when I want to move markers this way, or I want to move the markers as I've said, I need to make sure that I can do that without introducing new double recombinations, because when I'm moving markers, I might actually introduce new ones. So as I said, I can't just move this around in FlexQTL. So I could use just visually that. So if I wanted to move marker 739 all the way past marker 4331. So first I'm going to do is select everything again. And then I can highlight the two columns. So it was 7399 and marker 4331. And I wanted to move this marker behind this. Now you see that these, I can click on both columns by clicking on the first, holding Control down, and then selecting the second one. And these are now slightly highlighted. So what I need to make sure of is, as I'm scrolling through here, is that whenever here in this column there's a 0 or a 1, that there's not a recombination happening at the same time in between. Now here's a recombination happening in between, but because I don't know what this marker is, or where it's coming from, if I move this here, it would still not cause an issue. And so if I scroll down through this, I'm just looking for markers that, like this one, which have a 0, which have a call here and a call in this column, or anything in between, and that don't have a recombination at the same time. Now here we see another individual that, where if I move this all the way here, it would actually solve also this recombination for this individual. So this is great. So yes, I should probably be moving this marker around. These are the two individuals I saw before. And then as I'm looking through all individuals, I will not find an individual where I would cause a double recombination just by moving this to here. And that way I know now that I can safely move this marker behind this marker. And if I do that, I have to go into my data file and in my map file, and in both places change the order. Because if I only do it in my map file, remember that FlexQTL just assumes the marker order to be correct. It's not going to rearrange your data file. So make sure that if you move markers, you move it both in your map file and in your data file. There is one other way to do this. If this visual way in FlexQTL is not, if you don't like it, there's another way. If we go to our FlexQTL folder where our runs are stored, and this is the run, this is the project we did today, there are files called zip files, which stands for segregation indicator pattern, which is this here, segregation indicator pattern. So these files are also created in Excel. And you want to look for the ones that say population. So this is holding the data for the full collection for all your data. And you want to find the one that has the highest number, because that's the one that's the latest version and the correct one. These are just intermediate files that FlexQTL generates. So if I open this file, you'll see that it's very similar to what we've been looking at in Visual FlexQTL. It has dashes. If it doesn't know, it has ones, zeros, and zeros. Now at this point, this is not colored, so we want to color it. So we want to grab all our data, which starts here at cell E4, and by holding Control and Shift down and pressing down and right, I can select everything. And then under the Home tab in Excel, there's the conditional formatting, and you can say either new rule or manage rule. But by manage rule, we can add a few rules faster. So I'm gonna have this. There's no rules right now, but I'm gonna conditionally format, which means that I'm gonna set italic style to color styles depending on what their value is. And so I'm gonna say only cells that contain a value equal to 0, those are, and then I want to format it, and I want to click on this format, and I want to fill them in a certain way. So I think normally this will, the font tab will be open, but you want to go to the fill tab so you can say which color you want. And just to stay consistent with Visual FlexQTL, anything that is a 0, we want it yellow. And then we can keep adding rules to this, equal to, and we have S0s as well. So we want to format those in the lighter yellow. Say OK. and we add 2 more rules, and now for the ones, so this is equal to 1. We're going to format it in blue. Say OK, and then the last rule will be 4 S1s. So this is the S1s, and if we format it, we'll just take a lighter blue so that it's very consistent with Visual FlexQTL. And then you just say apply, or you say OK, and then you see that we get the same coloring as we did in Visual FlexQTL. Now I would add filters to this one, data and filter, so that we can filter on things here. And then I wanted to move marker 7339 all the way behind marker, I think it was 4331 here. So now I can do it, because in Excel we can move our columns around by using cut. And then if I want it to be here, I want it to have it inserted here. And now I said before, we only look at markers that have a 0 or a 1 or an S1, a colored. So everything that has a dash, we don't even have to worry about, because we can safely move that. So it's only the ones that have a color here that we need to look at. And now we can just, so that's why we only filter for those. And now we can scroll through this and just make sure that if I've moved this, that yes, there's yellow on each side or there's blue on each side if this marker, depending on which this marker is. And if we would do that and we would look at that, we would see that that works. The other thing that can work is if this is yellow and this is blue, but this is not yellow anymore. So a true recombination can happen, of course, can happen as well. But otherwise, we just want to we can just scroll through this. And because we filtered, we have to look at much less individuals. And then we can see that, yes, this all looks really great. We can move this marker to this position. And then we can go in to our data file and move our markers around. So that's one other thing that you can do. I've gone over this. Here are some few other examples. If you look at all these yellows, but there's blue, and then there's yellow, and then there's blue again. But if we would move this marker all the way up to here, anywhere after this point, that will work. And the same goes for any time it's blue. You can see that there's sometimes yellow around it, which would indicate a double recombination. But if you move it anywhere past this point, then that would work. And these are two examples. This is the marker I already talked about, and this is another marker, 2 markers that we could move. And there's plenty of those examples in the data set as well. You can see that sometimes these markers don't plus not really well either, so you probably want to make sure first that the genotype calls are okay. But then once you've done that and you still see double recombinations, that could be an indication that you need to move your marker. Now, I don't have an example of this in the data set I gave you. It's pretty rare, but I've said before, FlexQTL needs to determine which alleles are physically linked on the same chromosome, and sometimes it does that wrong. And so that's a phasing issue. I've only seen that happen. It's typically just one family. Typically, it's when the parent, one of the 2 parents doesn't have the grandparent or its parents in the set. So it's for a family for which the grandparents on one side are missing, that happens. And you see it because actually all individuals have a double recombination except 1 or 2 for which a regular recombination is occurring in that family. And so what would happen here if the phasing is an issue, then by changing all the zeros to a 1 and all the 1s to a 0, this would be solved. And you could see that that would be the case, because if this is all 1s, then just these are all just 1s all the time. And so everything would change. But also, this one where the recombination would change. And so this one would become a 0. And I zoomed in a bit on what's happening then. If this is how it is now, but if I change this one to a 0, then the recombination happens over a much bigger interval, or much more SNPs at least, than it does here. And I think that's why FlexQTL is incorrectly phasing it. It is because if it has the choice between a short interval or a long interval for true recombination, it's going to choose the short one. Now, if we've had the grandparents in our data set, FlexQTL would not have had that freedom to choose. But because we don't have the grandparents here, it has the liberty to choose, and it chooses incorrectly. The only way that I found to solve this is by making this individual in which the actual recombination occurs, by making that individual missing. It's not a big deal that we make it missing, because we are going to make haplotypes, and we're going to do some imputation with the haplotypes, and that value will most likely be filled in again. So it's just a temporary make missing, so that everything else occurs correctly, at least. And that's kind of it. I guess for the map, when we're talking about changing our map, I didn't really specify when it happened, but it's often only in a few individuals, and they don't need to be related. So it's often with the singletons, it's those markers that only occur, that are only in that list one or twice. And as I said, it's often characterized by a third recombination nearby, and by just moving the marker, we solve all the double recombinations at the time. So I want to reiterate here that I said first go through all the major ones. Start with the singletons, start with the ones that have a lot. Then once you fix those, go to the double recombinations file created by Visual FlexQTL, which lists all the ones in a certain interval, and then start solving the ones that for regions where there's a lot of double recombinations, and start solving those. And on regular points, when you solve a bunch of double recombinations, or when you think you solved a bunch of double recombinations, rerun it, because you might have solved more than you think. So it's true. This is truly an iterative process. And as I said before, as you're changing your genotype calls, don't forget to check your parent-parent-child errors, because by changing genotype calls, you might have introduced new parent-parent-child errors. But as I've said before as well, that those are often only a few if you did, and they're often easily to be solved. The other thing I wanted to point out is that unlike our parent-parent-child errors, which we kept resolving until there were none anymore, at least for the singleton, some of the double recombinations that are reported can be true, and you don't really need to read what is here, but there is a double recombination in this stretch, and it's not red, because it's over such a large interval that Visual FlexQTL actually thinks it could be happening, and it's not an issue. But it will still be reported in that file with the double recombination. So what we did for that is, if I go back to my master file, we kept a list of all the double recombinations reported by the singleton file, at least, that we looked into and that looked to be true. And we did that so that every time we do a reiteration and we relook at our data, that we don't go and investigate these double recombinations again. We've looked at them, they look true, and because they look true, we just put them in this list. And so next time I see them reported, I know I can ignore them because I've already looked at them. And you see that I also made some annotations. There were a few phasing issues I could not resolve by making values missing. But I can tell you that those will be resolved once we get to the haploblocks and haplotypes next session. So if you see a phasing issue and you cannot resolve it, you might also just keep it because they might get resolved. But these are phasing issues that occurred in only one or two individuals rather than in a whole family. So if it occurs in a whole family, as I showed you before in this slide here, then I would go in and solve it if you can. But for some of them, I could not solve it by just making data missing. And then there's two more points I want to make. I don't have examples for it. They occur very, very rarely, so it's not something you need to worry about too much, but you need to be aware that it exists. So the first is multi-locus markers. So in Apple, we have some SNP markers that map to multiple positions, and they cause double recombinations for some families. How did we know they map to multiple positions? That's not that easy to figure out. One way we knew is because in Frubidomics, they had a lot of bigger families. They made a big map, and they found that certain markers, depending on the family, map to different chromosomes. So they knew that certain markers from the 20K map to multiple locations. And some of those markers that did so are also on the 8K. And because they're also on the 8K, and because they reported it, I now know that they are on that they could be on multiple locations. So that's one. The second one is, I've showed you before, we have multiple genomes in Apple, so I've been updating the SNP positions, and I've been doing that by looking at the sequence of the flanking the SNP and by blasting that against the genome. Now, for a lot of sequences that gave rather unique hits. For some of them, that gave non-unique hits that map to multiple locations in the genome. And if those stretches that map to the genome on multiple locations are large enough, at that point, it means that the probe could bind to multiple locations in the genome, and that means that they're actually multi-locus markers. So from my BLAST results, I knew that there were certain markers that could map to multiple locations, and I noted that down. So when those markers were causing double recombinations, I checked whether the alternative region in the genome would work better. Now, for most of those multi-locus markers, multi-region markers, multi-chromosome markers, they cause some double recombinations in one family or in a few families. And then if you move the SNP to the other region, you solve those double recombinations. But then suddenly for other families, you will get double recombinations. And that is because that marker is truly assessing two loci. And so for some families, it's looking at one region in the genome, and for other families, it's looking at the other region in the genome. And so what I've done with those markers is when I found those, is I removed them from the data set. When they caused issues, I removed them from the data set because I could most of the time not make accurate genotype calls for both loci. Now, the other thing, and that's even rarer in Apple, or didn't even happen even less, is segmental aneuploidy. And if you recall from, I think, the second session, we talked about polyploids and triploids, and we also talked about aneuploids. And aneuploids were individuals for which acted as which are diploids for most of their chromosomes, but an aneuploid had only one chromosome copy or maybe 3 chromosome copies for one or a few chromosomes. So it acted like a diploid for most of its chromosomes, but it acted as a triploid maybe, or for one of its chromosomes. Now, a segmental aneuploid is even more complex. It's when basically it's when a large segment of a chromosome is missing. So it's acting as a diploid for most of its genome, except for this one piece here, where it actually has only one chromosome set. And that is actually, and that can be a large segment. And they cause issues too in our data sets, and they report errors. So there's 2 ways they get to errors. One is parent-parent-child errors. And that you can understand that by thinking if this parent that gave the shorter chromosome did have this piece here, and it just got lost in the next generation, but the parent had a BB allele here, then we would expect it to give a B allele to its offspring. Now, the offspring didn't get anything because it's missing a chromosome segment, and the other parent gave an A allele, so the true genotype of this offspring would be A nothing. But Genome Studio is not calling something A nothing, it's calling it AA. Well, our parent is BB, our second parent is BB, so AA and BB gives a conflict, and that's a parent-parent-child error. So those might lead to parent-parent-child errors, these segmental aneuploids. You would recognize that because the parent-parent-child errors are only for a specific stretch of the genome, only for that area where the chromosome part is missing. Now, it could be that if that leads to too many parent-parent-child errors or parent-child errors, that you've already discarded that parent-child relationship. If that leads to too many errors, you've, like let's say to 50 errors, you would have probably said, oh, there's too many errors. It's not, this individual is not the offspring of this parent. A way to solve that would be to adjust the R script and report parent-parent-child errors per chromosome, because then we would see that actually all our parent-parent-child errors are located to a single chromosome, and if we would look deeper into it, we would actually notice that it's only for a certain segment. I've started implementing that in the R code, which the one you got to check parent-child relationships, but I mean, there's a lot more work to get it done. If somebody is willing to work with that on that with me, always welcome. Send me an email. But that would be a way to solve it. The other thing that these segmental aneuploids have is they lead to a lot of double recombinations for the part where there's a chromosome segment missing. And again, you could look at this by, if you have an AB parent and it would have passed on its B allele, but it ended up passing on nothing because this part is missing, then this offspring would, and the other parent gave the A allele, then this individual again would be A nothing, and again it would be genotyped as AA. And to explain how this individual got its second A allele where it should have gone in the B allele, the only way to do that is by introducing a double recombination, as I've shown you in the example earlier. And so in a chromosome segment, this might happen a lot, where it needs to recombine and introduce recombination just to explain what's happening. And this is a case where it's happening in chromosome 9. And if you would, and if I can see, if I can zoom in a bit for this. But if you look at this, you would see here it's going from 1 to 0, which is the first recombination, back to 1, which is the second, back to 0, which is the third, back to 1, which is the fourth, and so forth. And there's 10 recombinations in a 20 centimorgan interval. And that's only happening for this specific region. Everything else is individual looks good. Its parents are matching everything. So this is a strong indication that this individual here lost a part of a chromosome. And that's why we're seeing all these double recombinations. So that's something that could happen too. We saw it 3 times in over 1,500 individuals in apples. So it doesn't happen a lot, but it can happen. So be aware that it can happen. And that's it as it goes for double recombinations. So just as a quick reminder, summary, look at double recombination, look at the singletons first, look at ones where there's a lot. And for those, check your genotyping calls. Once you've done that, go to the ones that, the second file that is created where it reports over sort of specific distance where multiple markers can be involved. Check those for regions where a lot of double recombinations happened, and then slowly make your way down to double recombinations that just occur a few times. Rerun things regularly, because by solving things you might be solving more than what you think. And the main causes for this, for double recombinations, are genotype call errors or incorrect positions in your map. Those are the 2 you really need to be looking for. Those are the ones that occur the most. The things that occur rarely are phasing issues, multi-locus markers, and segmental aneuploids. Keep in mind that they exist, but those should not be your first reasonings for fixing a marker. And that's all I have to say about double recombinations. So if there's any questions, you can ask them now, or you can just send me an email. And otherwise, I'll see you next week.
Thanks, Ben.